Hello and welcome to ML4 Q&A. For those returning listeners, my voice might not be familiar. I'm Chandana Rao, a second-year PhD student in quantum information, and I'm one of the new hosts of the show, along with my co-host today, Patrick.
Hi everyone, my name is Patrick Geraghty and I'm a third-year PhD student working on computational many-body quantum physics. We're really excited to join the ML4 Q&A host team and bring you stories right from the cutting edge of quantum research.
ML4 Q&A is a show where members of the Matter and Light for Quantum Computing Cluster talk about their careers, their research, and the future of quantum technologies.
Today, we're excited to welcome one of ML4Q's group leaders, Professor Daqing Wang from the University of Bonn. He's been at the forefront of quantum science, teleporting quantum information across 143 kilometers, tackling tough challenges in the lab, and creating stable single-photon sources by trapping individual molecules in microcavities at cryogenic temperatures.
In this episode, we'll explore his journey through these groundbreaking experiments, hear what it really takes to run such demanding labs, and talk about how collaboration across disciplines, especially between physics and chemistry, drives his work.
As a theorist, I really enjoyed learning about the day-to-day life of an experiment and learning about some unexpected sources of noise. It's also fascinating to hear how he, as a physicist, interacts and discusses with chemists in order to find useful molecules for experiments.
And we'll also look ahead to the future, how molecules and even artificial intelligence might help design the next generation of quantum technologies.
It's a conversation about the past, the present, and the exciting future of quantum science.
So let's dive into it.
Hello, Professor Wang. Welcome to the podcast.
Thank you for inviting me. I'm very happy to be here.
So, many of us as young researchers, we write in our LinkedIn bios or in our applications that we want to push the boundaries of science and technology. But then you are one of those whose resume actually reflects the same thing. Like just as a master's student, you were part of Anton Zeilinger's group and you contributed to the groundbreaking experiment of quantum teleportation, where you were able to do this teleportation over 143 kilometers between the two Canary Islands. So that was a very big milestone in quantum information. Could you take us back at that time? Like as a master student, what was it like to be part of such high impact project?
It was a eye-opening experience for me at that time as a freshman master student. So I was always interested and fascinated about lasers. During my bachelor study, I always want to involve in experiments that can play around with lasers. And later, I also found that with laser, you can do nice quantum physics experiment. That what drew my attention to the work of Anton during my bachelor study. And in my master's, I moved to Germany, and I wrote an email to Anton. I'm always interested in the experiment you are doing. And can I do an internship or master thesis work with you? And he was very kind to have accepted me. And I also told him I really like this experiment. Photons are sent over a longer distance, and this can be used for testing of quantum mechanics, for example, also for quantum teleportation. And he was very kind to offer me a chance to work in the lab. And for me, it was a new touch that you happen to realize even such kind of large-scale experiment is also being pushed by a rather small group of people. And when I was there, I asked what actually could I do as a master student. And they had problems that they need to fix. And one of them is about detection of these photons. So you have to imagine that you send photons over hundreds of kilometers across atmosphere. And this light, when it's collected by a telescope, it will not be focusing very well as you do it in a lab in a perfectly controlled environment. So there is a trade-off between selecting detectors. For example, if you want to collect all these photons, you need a larger active area because atmosphere disturbs the path of the transmission. But if you pick a detector with a large area, then you intrinsically increase the noise of this detector. So there's a trade-off between the size of the detector and the noise you can tolerate. So the very first task I did was to test these detectors, to focus the light into a very small spot, move across the active area, and try to characterize the performance of the detector and try to suggest okay, among the 3 or 4, this one is probably the best choice that we can take.
And in terms of this kind of experiment, can you give us just a broader sketch about what were they actually trying to do? So you're talking about sending these lasers across great distances. What was the just basic sketch of how this was set up?
So the motivation of this kind of experiment is to be able to send photons on the global scale, which lately has been demonstrated by putting photon sources on satellite, for example, and then you can, through this long-distance free space link, you can perform, for example, quantum key distribution or test of Bell's inequalities over large distances. But before this was realized, one have to, on one hand, really check that this is doable. For example, channel losses and the ability of tracking a moving object and so on. All these techniques put together can still make the experiment work. But and before this was demonstrated on a satellite, I think there's also kind of a mind block that people think that this probably is not going to be possible. And this 143 kilometer teleportation experiment can be viewed as one of the many efforts to show that will be indeed possible to bring this kind of quantum optical experiment to the global scale.
But if you want to extend the distance and do the same experiment in free space, then we will have problem because of the atmospheric turbulences and the same the thing which you mentioned, the trade-off between the telescope detectors and the atmosphere. How can we overcome this trade-off problem that we have if you want to increase the distance?
So there are 2 approaches. One is by putting source and detector on satellite and try to increase the collection aperture, so that even if the spot gets a bit bigger, you can still collect more. But this also has its intrinsic limits. For example, you are relying on the weather. If it's raining and cloudy, this won't work anymore. And the other route, which probably is going to be more practical, is to not using the free space channel, but by sending photons into fibers and having photons at the telecom wavelengths. And I think there have been very big technical advancement in the past 10-15 years in this direction, that you can extend also quantum key distribution, for example, on a scale of thousands of kilometers.
So working from such a macroscopic project, your PhD seems like you've moved to a very microscopic, microcavity area where you worked mainly on coupling these organic molecules into these Fabry-Perot cavities. So what was your motivation to choose this topic in your PhD?
Yes, the teleportation experiment is on a very large scale, and there we used photon sources that comes from spontaneous parametric down conversion. It worked well for this kind of experiment, but also these kind of sources are based on probabilistic conversion of photons. So it's hard to control that if you want a photon at time t equals to 10 milliseconds, you get a photon. So it's not possible with this kind of source. And then I realized you actually not only need light, but you also need matter if you want to make a device that can give you a photon at the time you wish. And this brought me to the research with solid-state emitters. And there you can take a material, and the material can have some defect. And in the system I worked on, these kind of defects are individual molecules that you can dop into a crystal as a dopant. And then you can optically excite them selectively, so one by one. And if you control it well, you can get nice photon emission properties from this kind of molecular emitters. And one application of it is to make deterministic photon sources.
So are you saying this molecular emitters have any other advantages than the already existing photon emitters that we have?
The molecule has its special property because there's not only one molecule, there are so many different kind of molecules that the chemists can provide. And if you talk to chemists, they can also suggest small modifications to a particular molecule that can fine-tune the properties of these molecules. And that's what I find interesting, because in a way atomic physics are very mature, well developed, but molecular physics, especially the techniques used in molecular physics, can be very different from one experiment to the other. One particular reason is that people have not found the general way to control molecules to the level that people can control atoms. I found this first a very challenging task, and second, you can speak to a chemist and you can get probably molecules that with the desired property that you need for an experiment. That's the second reason I think this area is appealing. And come back to your question about single photon sources, it is possible to identify molecules that emit in a particular wavelength range that lies between blue to near infrared of your choice if you look carefully enough in the space of possible molecules.
So then in terms of looking for these kinds of molecules, is this something that you go to a chemist and say, hey, I want these particular optical properties at these particular measurements, and kind of they go through and look through their entire cabinet and see if they have something that fits? Or is it a little more of an interactive process where you have to really design a molecule to try and get it to behave the way you want it to?
It's indeed more complicated than you simply go to a chemist and ask, I want a molecule that emits at this wavelength. What you get is normally a suggestion or a small table. These few candidates probably fit in this wavelength range. What you have to do is put them in a crystal and see whether you can see the molecular signal, whether you can identify individual ones, and whether they indeed emit at the wavelength that has been calculated. So there's a difference between calculations that you can do and the real experiment when you really put the molecule in the solid. It is not only an iterative process, but also the measurement we can do actually works as a feedback for the theory side to put more parameters in their model in order to get more accurate predictions.
But experimentally, how easy or tough is this to use molecules as single photon emitters?
The techniques that's used for exciting molecules detect fluorescence, it's very similar to other experiments, for example, with semiconductor quantum dots or with nitrogen vacancy centers in diamond. So what you do is you prepare the sample, you freeze the sample in a cryostat, and you integrate your sample into a cryogenic microscope. You look at the emission signal. The difference is for quantum dots, for example, you have a few candidates that work really well, and also for color centers in diamond, there's a few type of color center that works really well. And this is probably well understood. Where do they emit and what kind of branching ratio quantum efficiency you can get. And for molecules, because there are so many, it's there's no established database. Let's say saying if you pick molecule A, put it in crystal B, it works. There's a lot of space for both experimental studies and also for theoretical work in this direction, predicting the suitable combination of molecules and the host.
So you have received a best dissertation prize for your PhD. So I'm assuming this work is not obviously a very easy one of, integrating these molecules in a Fabry-Perot cavity and then using them as single emitters. So technically, was it very difficult for you to achieve this target?
I started my PhD in 2013. At that time, one challenge in the community is to integrate single emitters with photonic structures with high efficiency. And my PhD work was to couple molecules to open Fabry-Perot cavities. Open means it's a two-mirror cavity that you can freely tune the lateral position of the emitter, and you can also freely tune the distance between the two mirrors. The challenge has mainly been how to integrate the molecule into the cavity and how to have the whole system work stably at cryogenic temperatures. And on one hand, the community knows how to stabilize cavities if it's not in the cryo condition. On the other hand, the community also knows how to work with single emitters at cryogenic conditions. But putting these two together was a technical challenge, because to enhance the coupling efficiency, you want the cavity to have high finesse, and high finesse means you have to stabilize the system very well, because if the cavity drifts by a picometer or so, then your resonance is slightly shifted. And the difficulty on the technical side has been to tackle out or to identify individual noise sources in the lab, and this can differ from lab to lab, and then to control them and also to understand how the cryo system works. And I had a rather complicated cryostat to operate, and how these different factors affect the stability of the system and how to erase them from your system one by one. And at the end, if all these noises are being suppressed, then you could do the experiment. And that has been the main technical challenge I faced.
So for these different noise sources, they kind of, obviously they come from a very wide range of different places, but are they typically approached in trying to mitigate them? Are they approached by common methods, or was there a time in your PhD where you had to think of, oh, nobody's tried to get rid of this noise, I've tried all the usual tools? Was there a time that you took some new method to try and mitigate some of these noises, or is there an example of this?
So most of the noises is known from different communities. For example, you have ventilation noise from the ventilator. Then we have to call the facility manager. We want to do a test. Could you switch it off? Then we can compare the stability. There are this kind of noises. There are also noises, for example, in the crowd study, you have boiling nitrogen, liquid nitrogen. And we have found an interesting method to get rid of it out of trial and error. We found that if you fill in helium gas in the tank, that the nitrogen starts or stops to boil and will settle for a period of time. And that was the finding out of curiosity. I think till today we still don't understand how it works, but it worked. And it's probably interesting for someone if you have time to do this test by yourself and try to figure out why it works. But this has been one of the examples that we identified.
And so it was something about how while the nitrogen was boiling, the boiling nitrogen created vibrations in your system that was the source of the noise?
It was a main source of noise because boiling nitrogen is so strong, it creates a sound that if you listen carefully with your ear next to the crystal, you will hear it. Wow. And that is way too strong to operate this cavity.
How would you recharge yourself from to stay away from all this noise? In the sense, like outside the lab, how would you relax or do the extra things away from the actual PhD academic stuffs?
I think it's important to find your way to also get out of the problem in the lab. Yeah, I was in Erlangen and I had a good group of fellow friends where, for example, on Friday afternoons we will go to a beer garden, drink 1 or 2 beers together, and then we can complain about all different kind of problems we face on our own project. And that's been a good way of get yourself relieved from the pressure in the lab.
And also, what was your personal goal towards dealing with the failures or the success in the experimental activities during your PhD?
I think the key lesson I've learned is experiment can be very difficult, and difficult experiment has high risk to fail. And one need to have a strategy of determining whether this particular route is worth pursuing or not. Sometimes you found that, for example, this noise can be suppressed, but it will take considerably long time than you initially planned. Then you have to change your strategy. Maybe, for example, I can slightly change my mechanical design to get to bypass this problem, and the long-term goal is there, but you should try to be agile in the way that you approach there. And maybe at the end you would not be able to erase the noise by 100%. It's unlikely that in any experiment you would do a perfect job. But sometimes, do a 90% good job. It's not really bad.
So somewhere being optimistic helps.
It always helps to be optimistic.
So the other question I had was that typically a PhD is described as spending a finite amount of time to study one particular topic and know it absolutely in every corner and just really pushing the depth of knowledge. But also an important part of this is kind of opening your mind to what's the actual application of this. So when you were working on your PhD, what was the larger scope that you had in mind at the time, if you had this?
I think the main motivation for me to start on this project was a really interesting experiment. So after my supervisor introduced me to the topic, I have the feeling that it's cute, it's interesting, I have to do it. I have not thought about the application. And probably this applies to many fundamental physics experiments. You want to do that, simply you think that is interesting.
Are you someone who is more interested towards fundamental physics, like understanding what exactly is happening in the nature, or more towards exploiting these fundamental physics towards technology side?
I would categorize myself as a formal one of the formal side that I like to explore how sense works on the fundamental aspect, and if there are possibilities of applications that can come out from this work, and why not also spend some effort on there.
Right after your PhD, you kept a really big step of being a tenure track professor. So how was this initial moments, keeping this big step where you're away from your supervisor, and then you have to call the shots of selecting students, writing grants, and it literally opens a very new, diverse avenue for you to explore, because as a PhD, we are more concentrated towards research. But how was these initial moments for you?
I had a few years of transition time where I was a principal investigator in a collaborative research center at the University of Kassel, and there I could start a project on my own. I was very grateful when the CRC gave me this possibility, and you always start small. You start with the first master student you supervise. You start by first make a 1-year plan of what kind of preparatory work that is doable within 1 year and offer it as a master project. And later, if you acquire funding for a PhD student, you can start again build up on a slightly larger scale. This, I think, goes step by step. It's not a huge change that all of a sudden you have to face a big management problem.
And as a young professor, did you feel that you need any kind of supporting system from academia?
Yeah, when you start with a professorship, it's a lot of new things to learn. So how the academic self-administration works and so on. And you have to start to sit in faculty meetings. The work that you have to face is much broader than research itself. But both in Kassel and in Bonn, I had very good colleagues that if there's questions, I could pick up the phone, and I always get detailed answers and instructions that have always been very helpful and worked out wonderfully.
And how was your experience of hiring students initially?
I think it's important, if you want to start a team, you also engage in teaching. And the best students I got is always from my teaching experience, and especially at late bachelor and master level. And then you get students that are really motivated in this topic. That's what I would recommend for anyone who is starting individual research groups.
So, do you also look at other qualities beyond technical knowledge of the students?
Yes, of course. For example, to start a PhD project, I think you need to be really convinced that this is something I want to spend more than 3 years on and focus on this topic. The self-motivation is, I think, very important. And I believe in every PhD project you will face challenges, and you will probably be a bit depressed about it. And it is something that one has to think and really decide that I want to do this, and I will also be prepared to tackle this kind of challenges. And I think that's an important thing that you have to think about before starting a PhD project.
So your current research, it is an extension of your PhD work where you still use these molecules and you integrate them, couple them in the microcavities. And now you're also using this chirality property in these molecules. And how does these property help in quantum level?
Chirality is a very fundamental property of structures, and which also is an important property of molecules of certain structure. So from the fundamental physics and chemistry point of view, it's a very interesting topic to study. And it's also important and interesting to understand chiral molecules and their properties at the quantum scale. There are different reasons. On one hand, there's this concept of so-called homochirality, that the life on Earth, for example, is built with molecules, for example, sugar, which are chiral, and we do not understand why that we prefer only one part of the mirror-imaged molecules, not the other part. And this is a big topic that I think it's hard to understand at the end, but probably from the physics point of view, one can start by building simple, smaller chiral molecules, trying to understand them and look at their interaction with the environment. And on the other hand, doing molecular spectroscopy and also doing precision spectroscopy on chiral molecules can help understand the interaction of the electronic structure with the nuclei in the molecules. There has been a prediction of the so-called parity violation in molecules. It has been predicted since half a century that a left-handed molecule differs in the energy scales very slightly compared to a right-handed image of itself. And this is due to the weak interaction in the nuclei. Has been predicted but has never been measured so far. And if one were able to measure this, and this would be an important feedback to many theoreticians who have been working on the calculations so far to predict the energy scale, because it's also hard calculations. You need to integrate quantum chemistry, electronic structure calculations with calculations that involves the structure and properties of nuclei itself. So on this direction, doing precision measurement with molecules that are controlled in well-defined quantum state can also contribute to study of nuclear physics.
But does this have any advantage of using the system as a quantum emitter?
One might think that if you want to have circularly polarized photons being emitted by chiral molecules, one can potentially use chiral molecules for that. But typically, the chiral effect of photon emission by chiral molecules is only a very small effect, because the dominant one is still the emission led by electric dipole emission, and only the one order higher term in the coupling introduces a chiral signal, and that gives out circularly polarized photon.
And with these chiral molecules, so because there's this very slight difference in how you have to do measurements, are there entirely different techniques in measuring chiral molecules as compared to non-chiral ones? Or are there different measurements or different ways of doing measurements that are required when dealing with these particular molecules?
So there's a very big difference of making single emitters out of molecules. There you try to put these molecules in a solid state crystal, and you rely on cryogenic cooling. But if you want to do experiments that you want to be as precise as possible, then you cannot put the molecule in a crystal anymore, because you want to erase the environmental influence. And then you need to go to ultra-high vacuum. And there you typically have experiments that has very large vacuum chambers. You try to produce molecules and try to already produce them cold. Cold means close to their rotational and vibrational ground state, means on the 1 to few Kelvin level. And then you do spectroscopy on the fly while the molecule is propagating in the vacuum chamber. You shine in light. You look at either photons come out or electrons come out. So the experimental technique is rather different compared if you compare the single photon emitter type of experiment and precision spectroscopy type of experiment.
And then to be even more precise, because you're doing the spectroscopy with light, does the polarization of your light impact the chirality of the particle that you're measuring, molecule that you're measuring? And do you have to make a specific choice in this particular spectroscopy?
The interesting property of chirality-related measurement is if you want to measure a chiral signal, you need to send in a chiral excitation. So most of experiment on chiral molecules involving optics is done by comparing the response of the molecule to left-handed circularly polarized light and right-handed ones.
So if you want to use this system as a single photon source, then the non-linearity of that source matters a lot, as we have already observed in these waveguide related platforms. So in this system, how is the non-linearity?
So nonlinear optics typically is studied with pulsed lasers in bulk nonlinear crystals. And it's actually surprising or not surprising if you have a two-level system, there's an intrinsic nonlinearity, because the two-level system is not a harmonic system. And the difficulty of observing and using nonlinearity of two-level systems had been that you need to first couple your light very efficiently to the system. And if you can couple a propagating mode of light with a single two-level system with perfect, let's say 100% efficiency, and the series says you only need a quarter of a photon per lifetime in order to reach certain level of saturation of the two-level system and observe nonlinear effect based on this. And the prerequisite of doing such experiment is to make an efficient coupling. And this is hard to realize if you have a free space experiment and you try to focus your light very tight. And the solution to this is by integrating these emitters into small resonators where light is bounced back and forth so many times so that this interaction is enhanced. And the work I did in my PhD can be viewed as one of the experiments that demonstrated that indeed if you can put an emitter in a high finis, low mode volume cavity, that you can indeed bring the whole system into a regime where optical nonlinearity happens at single photon levels.
Also, how easy is this system to integrate into a smaller portable chips, let's say?
The original cavity design I worked on, it's hard to integrate in a chip because it's an open Fabry-Perot type cavity. You still have two mirrors, even if the mirrors are micrometer scale, but still for a chip integration is too bulky. Then you have to think about what kind of resonators you can make on photonic chips. For example, you can have micro ring resonators, and then we have to observe and see whether it's possible or which level of coupling is possible if you put the practically realizable finis of the cavity and mode volume of the cavity. And there has been a continuous line of work along this direction to try out to integrate molecular emitters onto photonic on-chip circuits.
So to go back to the nonlinearity that you were talking about here, could you give a brief example of what is a particularly nonlinear phenomenon that happens in these emissions?
Nonlinearity means if you send a weak light onto the system, and this weak light is enough to perturb the response of the system to a second excitation. And an interesting experiment you can do is optical switching at the single photon scale. So the idea is you send one beam into the system, which you use as a control beam. And this control beam, although being very weak on the level of 1 photon per lifetime of the emitter, is enough to considerably saturate the emitter. And in this case, if you send in a second beam, which you call a probe beam, that the transmission of the probe beam will be strongly affected by the existence of a pump beam or not. So if the pump beam is on, you can have the probe photon go through the system. If the pump photon is off, the probe photon will be reflected. In this way, you can view it as a photonic version of an electric switch. So that one signal controls the transmission of the second one. And the cool thing is that this works at the level of single photons.
So in your recent work, you described that single organic molecules as hybrid platforms for quantum technologies. So can you elaborate, what do you mean by hybrid in this sense?
The molecules by themselves are complex quantum systems. So it's much more complex than an atom because it has a structure that's formed by chemical bonds. And on one hand, this gives more degrees of freedom. So the molecule can vibrate. It has many vibrational modes. On top of that, a molecule in vacuum can also freely rotate. And this introduces a lot of degrees of freedom, and which traditionally have been viewed as detrimental factors for quantum optical experiments, because each of the energy level opens up a decay channel that an excited molecule can decay to. And this is traditionally been thought that we should try to find molecules that don't go into this state, which for an optical emitter makes perfect sense. But on the other hand, these states can also be used for quantum applications. For example, in atoms, you not only rely on a strong photoemission state, but sometimes you also need a metastable state, an excited state that lives for sufficiently long enough time, as, for example, qubit state for quantum computing. And the reason that we describe molecules as a hybrid system is this many different energy level of molecules. Some of them can be used as a resource to provide metastable state and with potentially long enough coherence time for applications on top of being a single photon emitter. For example, you can think of using molecule for a spin-photon interface where you can create entanglement of an emitted photon with the internal state of the molecule. For example, you can take the spin state of the molecule and try to again put the molecule into a cavity, and the molecule can be in two excited states, either on the singlet side or on the triplet side. So these are two different spin states of the molecules, and depends on the state of the molecule, it is coupled to the cavity or effectively not coupled to the cavity. And if it's coupled to the cavity, a photon come in because of the coupling of the molecule with the cavity will get reflected. And if it's not coupled to the cavity, the photon will get transmitted. In this case, you also get a kind of switch, but it's a switch that's defined, the knob is defined by the internal spin state of the molecule. And by coupling this to a photonic mode, you entangle the which pass information of the photon with the internal spin state of the molecule. In this case, you are also making a spin-controlled optical switch.
It was really helpful for us to know that molecules are not just what researchers from the field of chemistry work from, but we are also imbibing that into our quantum technology related aspects. But currently, what is exciting for you in your research field?
I think there have been exciting development in both directions that our group is working on. One is on integrating molecules into solid state structures and try to make quantum photonic devices. And along the other aspect, we are trying to also control molecules in ultra-high vacuum. And this is one of our key efforts planned in the second phase of ML4Q. There, our aim is to be able to control diatomic molecules to an extent that's almost as good as one can control atoms. And the idea is to use these molecules as qubits. And because molecules has more degrees of freedom, and one degree of freedom which is promising as qubit is their rotational states. So you can think of molecules being cooled to very low temperature in ultra-high vacuum and being held also fixed in position by a focused laser beam. And there's a small rotation that the molecules still can have. And this rotation of degree of freedom can be used as qubits. And that we are very excited to see how this works out in the coming phase of ML4Q.
So when you said you want to integrate them to the photonic devices, what are the areas that you are focusing on?
Yeah, the current big limit of integrating molecule to photonic structures is a hosting material. So far, people have found molecules work nicely if you put these molecules into a crystal of a similar chemical structure. But these crystals are not very stable in a physical and also in a chemical sense. So they are not resilient to common fabrication routines. They might get dissolved in organic solvents and so on. And one focus of this field is try to find new host material for the molecules. And one of the promising ones that has been recently identified by the community is 2D materials. For example, you can try to integrate these molecules in hexagonal boron nitride and see how well they behave. Do they emit photons as stable as they are when they are in the crystal and so on? So this is one of the fields that we are starting in collaboration with partner groups in Cologne and Aachen. And we're also very much looking forward to see what comes out with molecules integrated in 2D material structures.
So there are a lot of options for you to look around for the substrates or the molecules. Is there any way that you can make use of machine learning or AI to screen out the materials that are helpful to you?
I think that's one of the key research direction that we are heading on, there are so many different kind of molecules, and it would be hard for experimentalists to test one by one. And if on top, you have to think about the hosting material, and there are also so many different type of possible hosting material. So what we are trying is a collaboration that we aim to establish between experiment and theory, that we collect the database of all the known host-guest combinations that have worked so far and try to fit this eventually into your machine learning routine and see whether AI can give us some interesting combinations that we can test out in the lab. We have just started such an effort with a theory group at the Technical University of Vienna, and as a first step, we did a screening of a known database of molecules. And interestingly, this screening has predicted a few molecules that might work well, and we are going to test them out in the lab.
That's really interesting to know. And because you work in experimental field, and every areas in this experimental physics has its own difficulties to deal with. So personally, how do you define success in your research work?
I think success is something that's very hard to quantitatively define, and also it depends on which time scale you look at it. I think I would be thinking myself of being successful at the end of my career when people coming out of my team has found that the experience they had in my team has been useful in their career.
So we can kind of summarize that your student success is your success.
I would say so.
That's really interesting to know. And also in future, where do you think this molecular technology can take us to?
I'm very curious to see whether one day that the field can develop into a stage that if someone said, I want a molecule with this property and for this application, and the machine, you enter a code, you enter a requirement, and the machine would suggest you something out. That's a big unknown, but a very exciting unknown.
So one of the other things that your work has been connected with is something called quantum networks. Can you give us just an introduction? What is a quantum network to you, and maybe how is this related to the work that you've been doing?
To my understanding, a quantum network is an architecture that you can use to connect small-scale devices at distant locations. For example, you can think about connecting different small quantum processors. So nowadays we are, as a community, are able to create quantum computing processors at, let's say, rather large scale, but not enough to tackle realistic computation tasks. And this, on the individual scale of the devices, it will continuously increase. But eventually, to solve real problems, we have to wire up these individual processors to be able to use their collective power. And this requires the development of quantum links. And the development of quantum links, I think we can borrow inspiration from the classical computing platform, where communication between processors can be done by optical fibers. I think this has been the main motivation of quantum network-related research, that you try to perform or realize this kind of interlink at a quantum scale. You have individual atoms, molecules, superconducting qubits as the individual node, and you try to link them using photons in the visible wavelength range or microwave photons. Try to create entanglement of photon with a stationary qubit, and then you try to deliver the photon to another location and have it interacting with another photon or with another stationary qubit, so that you can create entanglement between distant qubit platforms.
And so this makes sense connecting with visible photons, but then what's the particular benefit of using molecules in this case in order to provide this link as part of your quantum network?
So molecules in this case can contain qubits, for example, the spins in the molecules. On the other hand, depends on which element you put in the molecule, the emission wavelengths can also be tuned. For example, there's ongoing work where mostly chemists try to tailor molecules with rare earth ions in the molecule. For example, one can think of integrating erbium ion into a molecular structure where a ion is being trapped but not in vacuum, but by ligands being bound on the side, and then you can embed these molecules into crystals. And in this case, these molecular emitters will emit, for example, in the telecom wavelengths, and at the same time, they also have a ground state which features spin degree of freedom, which can be used as stationary qubit. So this is something that you can both tune on the optical side, but also on the stationary qubit side. And that's what I found pretty exciting. And I also think the field is at its start of merging expertise from chemistry with those in physics and information technology.
And then also in connection with telecom usage, one of the useful things, as you said, is tunability, but then an also useful thing is stability as well. Are molecules in particular better for stability in this way, or other platforms?
I think molecules suffer the same problems as all other solid-state emitters. This comes from, for example, noise in the crystal. This can be electric field fluctuations in the local environment or local strains, and so on. And I think the development of the field is trying to understand this influence and trying to tackle them after I have discovered what is the main reason of the cause. And with molecules, there's one difference compared to, for example, MV synthesis diamond is the crystal the molecule sits in are normally a van der Waals crystal. So there's no covalent bonding in this case. And this relatively weak van der Waals bonding still allows the molecule to be treated as a molecule by itself. So there's no hybridization of the orbitals with the crystal. So the coupling to the bars, to the phonon and vibration bars of the crystal is slightly weaker. But this does not solve the intrinsic problem. It's still embedded in a solid, and it's affected by fluctuations in the solid. And one way is to go to even lower temperatures. For example, there are currently experiments that are done at dilution-free temperatures, whereas most previous experiments with molecules were carried out in a normal liquid helium cryostat between 1 and 4 Kelvin.
Professor Wang, thank you very much for sharing your journey, your experiences, and your insights with us today. It's been fascinating to both of you about science, the stories behind it, how these are all connected, and I'm sure our listeners will take away a lot from your insights and take some benefit. We look forward to following your future discoveries and see how the rest of ML4Q and the rest of your career goes. So thank you very much.
Thank you.
Thank you for having me here today.